Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is to introduce you to a concept called coefficient of friction. Alright, and before I start talking about friction, what I'd like you to do is I'd like you to find a textbook or maybe a coffee cup, but preferably a book, and put it on the table in front of you. And what I'd like you to do is just with your finger, kind of like my picture indicates, very gently push on the book and start with a very, very small force. And then push a little harder, little harder, little harder, and pay attention to what happens when the book starts moving. So I want you to pause the video, get the book, perform that experiment. Push a little harder, little harder, little harder until the book starts moving. Okay, presumably you have done that experiment for me, and now I'm going to talk a little bit about it, and hopefully, you know, what I notice or what I talk about here is going to be consistent with what you noticed. Right? What you should have found is that when you pushed a little harder, little harder, little harder, you should have found that eventually the book started moving, started sliding to the right. And you should have found that it took a little less force to keep it moving. You should find that the force kind of fell off a little bit. Now, what we're going to do is I'm going to do a little kind of thought experiment here using my little book as an example. If we look at the forces acting on that book, let's say we apply a 1 Newton force on that book. Then we could represent that with a force vector. Which I'm going to call F here. And if that force was 1 Newton and we do not observe that book to move, we would know that the net force on the book still needs to be 0, which means that my picture is missing a force. And the other force is what we would call frictional force. That force would be applied along this surface, and it would be in the opposite direction. Whoops, make that a little easier to see. And that force will be in the opposite direction of the applied force. Now, before we move on, there's a very important fact here. It needs to be clear that if this force is 1 Newton and the book isn't accelerating, this force is also 1 Newton. If this force is 2 Newtons and the book's not going anywhere yet, this force also must be 2 Newtons. So what I'm going to do here is draw a little graph now with the applied, whoops, nope, not that one. With the applied force on the horizontal axis and the frictional force on the vertical axis. Right? And I'm going to start actually with 0. If the applied force is 0, this force would be 0, so we'd be here on the graph. Right? If the applied force were, say, 1 Newton, the frictional force would be 1 Newton. If the applied force were, say, 3 Newtons, the frictional force would be 3 Newtons. And what we would get is we would get a perfectly linear graph. So I'm going to go ahead and sketch that. This graph is going to look something like this. Now remember, eventually the book broke free, and that means that the frictional force has a maximum value. That's as high as we're going to get on the graph. And once the book breaks free, you should have experienced that the force that you applied to it fell off a little bit. It takes a little bit less force to keep it moving than it does to get it moving. So on this graph, once the book starts moving, the frictional force falls off. So we're going to get a graph something like this. It's important to notice that this graph really has 3 things going on. We have this first region here where the frictional force is just equal to whatever I'm applying. Then we have this point right there. That's a very important point, and that corresponds to the maximum possible frictional force. And then we have this point here where the book is sliding. Most of the problems you're going to look at in a college physics text or maybe even a engineering physics text are going to be about this stuff here. Problems where the frictional force is a maximum value, or we're talking about a sliding frictional force. The maximum value of the frictional force is described by what's called the coefficient of friction. The coefficient of friction is usually denoted with this symbol, Greek letter mu. And the frictional force, it turns out, depends on the normal force. Number one question I get when I talk about what the frictional force depends on, the number one answer I get is the weight. Like if I made a larger book here, you'd get a larger frictional force. Well, that's true, but if I applied a force down, say 20 newtons, that also would increase the maximum frictional force without including the weight of the book. Or without changing the mass of the book. It's actually the normal force that's important. Larger normal, more friction. So the maximum frictional force is equal to this thing called the coefficient of friction times the normal force. Frictional coefficients come in two types. You have static and kinetic. You use the static coefficient of friction when you're trying to find the maximum possible frictional force. You use what's called the kinetic coefficient of friction when you're trying to find the sliding frictional force, or what's sometimes called the kinetic frictional force. So I'm just going to put sliding friction is equal to the coefficient of kinetic friction times the normal. All right, so we've got this new thing called the coefficient of friction. What is it? Well, simply put, it's the material dependency of the frictional force. Mathematically, what it is, it's really just a percentage. If your coefficient of friction, for example, was say 0.2, it means that if your coefficient of static friction, let me be more specific, was 0.2, it means that your maximum frictional force is 20% of the normal force, or 0.2 times the normal. If your coefficient of static friction is, say, 0.9, it means your maximum frictional force is 90% of the normal force. Frictional coefficients have no units. You'll notice that the frictional force is measured in newtons, but the normal force also is in newtons. So they're dimensionless things. So they're basically percentages. Frictional coefficients usually are bound between 0 and 1. I say usually. They're almost never perfectly 0. They're really almost never perfectly 1 either. They're usually, I really should put probably strictly less than 1. Most frictional coefficients fall in this range. I say most. There are some cases where the frictional coefficient actually is equal to 1. In some cases even a little bit higher. And I'll save that for other videos as far as what type of cases will your frictional coefficient be greater than 1. But to kind of summarize this as quick as I can, the frictional coefficient is the material dependence of the frictional force. Right, different materials on different materials will have different coefficients of friction. For example, a hockey puck on ice would have a very low coefficient of friction. However, a rubber tire on a concrete road has a very high coefficient of friction. Right? What are they used for? They're used for calculating the maximum possible frictional force and sliding frictional forces. And what they do is they relate the frictional force to the normal force. They're typically values you can look up. You can go through your textbook there, and I'm sure in chapter probably 4 or whatever the chapter is in Newton's laws of motion, you'll find somewhere in there you'll find some tables with some frictional coefficients. So I think that's enough for now. I think I'll just start making some videos on how to use frictional coefficients in problems. Have a great day.